Hello, Mrs. Boyd here, and today we are going to talk about how to use dimensional analysis to solve conversion problems. This is also a powerful technique to use throughout all of biochemistry. Even if you have equations and you can't remember what the units are for something, you're gonna learn a lot today about how units can help you solve lots of math. So let's begin with the definition. The analysis or dimensional analysis is defined as the analysis of the relationships between different physical quantities by identifying their units of measure and tracking these units as calculations are performed. So, couple key things here. We're going to have to understand the relationships between different physical quantities. We're going to have to spend a lot of time playing with units and keeping track of these units as we do calculations. So let's jump in and see exactly how it works. So the example we're going to start with is how many eggs are in 5.5 dozen? So the first thing you always do when you're given one of these problems is you're going to write down what is given. So 5.5 dozen is what's given. We can always put that over 1. Then we're going to put a multiplication symbol. And then I'm going to put a box for our conversion factor. All right. So the conversion factor, that just means what is the relationship between a dozen and egg number? Well, of course, you will all easily know that there are 12 eggs in 1 dozen, right? Even a kindergartner knows this. So this conversion factor is very simple. So we're going to go ahead and set that up. 1 dozen is related to 12 eggs. That's the relationship. Now you're probably wondering, how did I know to put the dozen on the bottom and the eggs on the top? Because this is really important in dimensional analysis. The reason I knew that is because I have to have dozen cross cancel. Those units have to cross cancel. I call it the crisscross rule. So I knew dozen had to be on the bottom because I need my end answer to be an egg. So the only thing I want left in terms of units is eggs. So I knew my dozen had to go on the bottom because I have to get rid of it. All right, so let's just go ahead and do the math now. That's all that's left. So we're just going to multiply across the top and across the bottom. So 12 times 5.5, and don't be shy. If you need to use a calculator, go for it. So as soon as my calculator pops up here, come on, my little friend. All right, 12 times 5.5 equals 66. So I know that there are 66 eggs. And that's going to go on the top. Oh, excuse my stylus here. Matter of fact, let me just make that a little clearer. Oh, I love that about Notability. So 66 goes on the top. And then to get the number on the bottom, you are just going to multiply 1 times 1. Again, you just multiply across the bottom. Don't let this math scare you. 66 divided by 1 equals 66 eggs. And that is our answer. All right, let's try for something that maybe is a little less intuitive. So in the lab, we might be asked how many microliters are in 0.2 milliliters. Because we don't have anything in the lab that can accurately measure 0.2 mils, I mean, all of our graduated cylinders won't measure that. And we may not want to use a serological pipette. So we're just going to go ahead and translate that into microliters. Might be easier to use a micropipette. All right, so let's see how this works. Again, same philosophy as before. Always start with what's given. 0.2 milliliters over 1 times, and then we're going to put our conversion factor in the box. So let's take a look at our conversion factor. We know we're going from microliters to milliliters. If you don't have this memorized yet, I do have a handy little chart down here. So we know we need microliters and we need milliliters. So let's see if we can find which one of these 5 conversion factors is the correct one. So aha, here it is right here. Microliters to milliliters. Why? Because I see a micro, I see a milli, and anything can go into those blanks after it. So microliter, milliliter, could have also put seconds there, meters, grams, anything your problem gives you. That's the beautiful thing about the a metric system. It's all in tens and it always uses the same prefixes. Okay, so we have a relationship of 1,000 microliters is 1 milliliter. So let's pop back up here. And let's just go ahead and start off by putting our units. We know ml has to be there. We know microliters has to be there. Why? Because the crisscross rule. We have to have milliliters on the bottom so they can cross cancel with the milliliters on the top. And then we know now the numbers. We know that there are 1,000 microliters in 1 milliliter. So let's go ahead and again just do the math right across the top. If you need a calculator, don't be shy. 0.2 times 1,000. I just happen to know that that is 200. I've gotten kind of good with moving the decimal, but again, just punch into the calculator if you're at all concerned. And then 1 times 1 across the bottom is 1, and that equals 200 microliters, because that's what we needed to find. Those were the units that we had to convert it to. All right, let's do our one final one here. How many grams in 120 milligrams? So again, just like before, we start off with what's given. So 120 milligrams over 1 times the conversion factor box. Again, if you don't have that memorized yet, no problem. I have it written right down here. We know we're going milligrams to grams. And let me change my pen color so you guys can follow along here. It's this one this time. Because again, we have milligrams to grams. All right, so let's go ahead and plug that now conversion factor that we know up here. Again, you can always feel free to start off with the units. And we know that we have 1,000 milligrams in 1 gram. Go ahead and cross cancel. Crisscross rule tells us to get rid of those units. And then again, we just multiply across the top. So 120 times 1 is 120. And then 1 times 1,000 is 1,000. And in this case, it does have one extra step because we are left with 120 divided by 1,000. Again, don't be afraid to use that calculator. And the answer is 0.12. So 0.12 grams. And that is our answer. So the beautiful thing about dimensional analysis is, did you ever have to remember which way to move the decimal? No. Did you ever have to remember how many decimal places to move? No. It takes all of the guessing out of it. If you set up your dimensional analysis problems every time like this, where you do what is given multiplied by some kind of conversion factor set up to obey the crisscross rule, then you will always get the right answer. So hopefully this will be helpful for you and aid you in lots of other dimensional analysis type problems that we will have in biochem.